Welcome to the Part 1, the Foundations of Symmetry. Group theory is fundamentally the mathematical study of symmetry and transformations. Let's ground this with a simple shape, an equilateral triangle. We can perform certain actions on this triangle that leave its overall footprint unchanged. First, we simply do nothing. We call this the identity action, denoted by E. Second, we can rotate it 120 degrees clockwise. We denote this rotation as R. Third, we can reflect it. Imagine a vertical axis down the middle. Flipping it across this axis is our reflection, S. These actions can be chained. If we perform R twice in a row, we rotate it 240 degrees, which we write as R squared. And if we rotate it 3 times, R cubed, we return exactly to where we started. This behaves remarkably like an arithmetic system. Before formally defining a group, we need 2 components. First, a set. A set is simply a collection of objects, like integers, the real numbers, or the symmetry actions of our triangle. Second, we need a binary operation. Think of a binary operation as a machine that takes 2 elements from our set, say A and B, and combines them to spit out a single result, A star B. For this to work, the operations must satisfy closure. This means the output must always live inside the original set. 1 plus 2 equals 3. Addition on integers is closed. 1 plus 2 is 3, which is still an integer. But division is not. 1 divided by 2 is 0.5. It escapes the set of integers. We are now ready to define a group. A group is a set combined with an operation that satisfies 4 strict axioms. Number 1, closure. Number 2, associativity, meaning the group of operations doesn't matter. Number 3, an identity element exists. And number 4, every element has an inverse that undoes its action. From just those 4 rules, profound structures emerge. For instance, a group can only have precisely 1 identity element. If we suppose there are 2 identities, E and E prime, then applying them to each other forces them to be exactly the same object. Similarly, inverses are unique. No element can have 2 different inverses. If we assume A has 2 inverses, B and C, we can look at the expression C star A star B. By shifting our parentheses using associativity, both paths evaluate down to show that B must identically be equal to C. For finite groups, we can map out every possible operation in a grid called a Cali table. This reveals hidden patterns. First, the Sudoku property. Because of our inverse rule, no element can ever repeat in any given row or column. Second, if the table is perfectly symmetric across its main diagonal, it means the order of operations doesn't matter. We call such a group abelian. To summarize, here are 2 classical examples. First, the integers under addition. The identity is 0. The inverse is negative A. This is an infinite abelian group. Second, the general linear group of invertible matrices under multiplication. Here the identity is the identity matrix. But beware, matrix multiplication is not commutative. This forms an infinite non-abelian group. Next, we will explore the deeper arithmetic properties that govern these systems.